Okay, so yeah, let's get started. Um, the UV spectroscopy measures how much a substance absorbs light based on its excitation and response to UV radiation. Yeah. Because response allows molecules to spread out energy and thus absorb more light, the MCAT frequently uses UV spectroscopy as a proxy for measuring conjugation. Hmm. So we know that conjugation happens in the aromatics, and that is where UV spectroscopy will be used. So we expect to face some questions on that. Then we have p-value, which represents the probability that results are due to random chance. So a p-value of 0.05 means there's a 5% chance that the results are due to random chance. For many fields of psychosocial research, this value and anything smaller than this value is considered acceptable and is therefore statistically significant. So if you have a p-value of less than zero point zero 0.05, then that result is statistically significant. And yeah, so you want less and less percentage to be due to random chance, and you want it to be effective the study, right? And we have observational study, where this study design is one where the participants are observed and the outcome is measured, but no direct attempts to impact the outcome is made. So you just observe it, right, from distance. You just see uh, the participants and you measure the outcome. And you do not make any direct attempts to impact the outcome. It means that we should be looking for some studies where you try to directly attempt to impact the outcome, like an interventional study, right? You have mass spectrometry, which uses a magnet and electrons to separate molecules into their components by mass to charge ratio, m over z. The height of the peak tells you how much you have. So tall peaks equals abundant ion. Now let's take a look at mass spectrometry. Yeah, this is a good one. This is what you usually see. You see the peaks, right? And the peak, like the Z, is one number less than what you see on the peaks. So if it's, or maybe one more, because this has three peaks, but it has a Z score of 2. This also has a Z score of 3, which should mean, okay, it's a different story. I forgot what these were about. And this is the technology behind that. So you inject some gas from the back. You have the electron beam, and you have a sample vaporizer, a heater, and the sample, I believe these are electrons. They just go through they're accelerated, they go through the tube, and there is a magnet here where there is a negative charge and a positive charge. So you expect the electrons to deflect towards the positive charge. They are attracted by this, and also they are repelled by the negative charge of the magnet. And the detector is what gives you these graphs, right? So you can see here that the magnetic field deflects lightest ions most. So you expect the most deflected ions to be the lightest because they move really fast, right? Because they're small as well and they move really fast. And that's why when you have less mass, you're deflected the most. And when you have more mass, you're not deflected that much, right? Let's take a look at this one. So there is the ionization again, the ion source, the electron beam, the insulator, the slits, you have the accelerator plate, you have the magnet, and you see that the deflection takes place here. The ions that are too light bend too much, and ions that are too heavy, they bend too little. And this is called the flight tube. And this is also to vacuum the pump. The only ions of the right mass can enter the detector, and these are the detector slits. And there's a detector here where it shows the graph on the mass spectrometry graph on the recorder, and last stage is the fourth and last stage is the detection stage. And let's put this in our notes. Let's put this one too. And maybe this one too. So you can hear that the O18 with the H2 has more mass, so you expect it to be deflected more. So it's a heavier molecule. And then you have O16 H1 H1. This should mean that this one has less mass. No. Oh, this is because it's O18, right? So 18 plus 2 ones is equal to 20, and 16 plus 1 and 2 is 19, then 16 plus 1 times 2 is 18, and 16 plus 1 is 17, and 16 is 16. And we can put this here too. So the mass to charge ratio is same as M and Z, right? So M is for the mass and charge is for Z. So the charge part should mean that yeah, you expect you see that the H has a plus, so yeah, we can figure that out later. Okay. Oh, I'm assuming there should be something also about the relative intensity percentage, but we'll figure that out later. Okay, back to the types of studies. We have the longitudinal study. It's an observational study design where participants are watched over a significant period of time. Is there a long term correlation between participating in violence in video games and carrying out acts of violence in real life? The MCAT will not make you split the hair on how long is long enough. If it's longitudinal, the time period that will have passed will be years. Okay, good to know. And again, for example, this is a longitudinal study. You want to see the long term correlation, like in years, between participating in violence in video games and carrying out acts of violence in real life. A really good book that uses statistics and these types of longitudinal explains these types of longitudinal studies has been there's a book by, I have it on my desk too, by Seth Stevens Davidowitz, and the name of the book is Everybody Lies: Big Data, New Data, and What the Internet Can Tell Us About Who We Really Are. It's a fascinating book, and the foreword is also by Steven Pinker, and one of the many noble minds that have advocated for this book. It's a fascinating book. I recommend everyone to read it. Okay, not to go off tangents. Let's go to the next concept. We have infrared spectroscopy. So we had UV spectroscopy, and now don't confuse it with the fact that for mass it was mass spectrometry, right? You can see here mass spectrometry. You do have a metric system for mass, but for the lights it's spectroscopy. It's like colonoscopy. Whenever you have a scopy, like scopy, at the end of your term, it refers to the fact that it's related to light, or like, yeah, light. Um, they didn't call it mass spectroscopy because for mass, it's there's no light playing out here, right? It's a bunch of electrons interacting with a magnet, and the magnet deflecting them. So yeah, and back to infrared. So it uses an electrical field to force dipolar bonds, whatever that is, we'll figure that out, to oscillate at a specific frequency and recorded at resonance frequency. When they vibrate is determined by strength of the bond and molecular weight of the bonded atoms. That was a grammatically incorrect sentence, but let's see what we're talking about here. Firstly, let's take a look at infrared spectroscopy. Oh, so this is IR spectroscopy, right? Let's see first how it works. So you have a light source, then you have a diffraction grating, which projects it to a slit, and you capture the infrared. Makes sense. This also can remind you of the Pink Floyd album cover. So yeah, you project that, you pass the infrared through the slit, and you get what is the infrared spectroscopy. You can see here that in the visible range of lights, what do you call this? I forgot. In the visible wavelength, you have ultraviolet, which is in higher frequency, and infrared in higher wavelength. So, and wavelength and frequency have reverse opposite relationships. What else are we talking about here? So you have an infrared light source, you pass it through the sample, then you have a detector, and that is what is recorded. And about the recordings, you note that the inverted peaks. The top is 100% transmission, and the bottom is 0% transmission. So from the get-go, you can assume that the bigger the molecule is, you expect it to transmit less, right? And there's also the wavelength, the wave number you see here, which is like the frequency. Because it's inverted, it's 1/centimeter. It means that it is hertz, and it is same as frequency. So you assume, like, the more you go to the right, the you can see the less the frequency and the higher the wavelength. So the more you go to the left, when you start from the left, it's a really low wavelength and the frequency is high. Now, what types of molecules would you expect to have high frequency, and what types of molecules you expect to have high wavelengths or less frequency? We'll figure that out. You have the typical infrared absorption values for various types of bonds. And you can see here that there are some examples. There is the NH stretch. So these on the left, they're in the high frequency range, and these on the right, they are on the low frequency range. So why does a C double C CO bond, a CO double bond, um, have the lowest frequency, and why does the CH bond, for example, or the NH stretch have the highest frequency? And also, there is something about the transmission. Which molecules do you expect to have the most transmission? Like CH stretch, for example, has a long transmission, which means that it is being transmitted less and less the longer the inverted peak is. Let me just set my set my timer for the next 1 hour. That 30-minute timer was for yesterday, where we had to finish. So we already did 3 time slots from yesterday. Now we are on our 4th one. I try to keep these time slots in between 90 minutes, plus or minus 10-15 minutes each. So yeah, we have a bunch of questions here, and we will try to figure that out. And let's take a look at here. You also want to take a look at ultraviolet spectroscopy. You have a light source. Again, should be the same, right? You have the wavelength selector, and this is also like, I remember this from you should also remember this from organic chemistry lab if you have taken it. And you have the chemical information source, you have the transducer, you have signal conditioner, you have the display system, and yeah, so you okay, it's high resolution now. Where does this thing start? Okay, you can see that it is only the infrared spectroscopy that has inverted peaks. For UV, it is about absorbance and wavelength. It's kind of more simple, and this should be. So you have a light source here, and you put the sample in between, and you have a light guide at the bottom of it, and then this whole thing projects it to a mirror. This mirror should deflect the light onto the DVD-R diffraction grating. You also need to know what is diffraction. And there is a detector that detects the UV light. Then there is the higher energy side of the electromagnetic spectrum, and this is on the right side, and I'm just trying to fully understand these concepts so that we will not face any surprises about the knowledge gap. And here it says when they vibrate is determined by, like, is it the vibration that is determined by strength of the bond and molecular weight of the bonded atoms. So if you remember, if you go back to infrared spectroscopy, you can see that these double bonds are in the middle, triple bonds. Then like the single bonds are on the left and also on the right. So it's about the vibration, right? The strength of the bond and the molecular weight of the bonded atoms is what determines the vibration. Basically the frequency. That's interesting. That is actually interesting. And you use the electrical field to force dipolar bonds. Okay, what are dipolar bonds? We can write our questions here like usual. Where are we? Separation techniques, lab techniques. Okay. Okay, just a second. I need to make sure my accounts are synced. You can take a sip of water. Okay, perfect. We have lab techniques. Let's leave it at that. And our question is, what are dipolar bonds? So you use the electrical field to force dipolar bonds to oscillate at a specific frequency, so they vibrate. Oscillation and vibration should be the same thing, at a specific frequency, and record it at resonance frequency. What does it mean that in infrared spectroscopy an electrical field is used to force dipolar bonds to oscillate at a specific frequency and recorded at resonance frequency. So it is oscillated at a specific frequency and it's recorded at resonance frequency. We'll figure that out. For infrared, let's put some pictures. Nanoscale infrared spectroscopy. That is interesting. Is this a different kind? Still don't know why it is inverted. Why is IR spectroscopy inverted? Has inverted peaks. Excuse my yawning. So we have a pulsed turnable IR laser. It's guided onto the sample surface. Then you have the IR laser is made collinear with the 532 nanometer detection laser. Then you have the collinear beams are focused on the sample surface through a microscope objective. And then you have when infrared absorption occurs, the photothermal response of the sample surface is monitored by the green detection laser. Then the reflected green light returns to the detector and the IR signal is extracted. Is this different than... Oh, so these guys are trying to break the limits of traditional infrared spectroscopy. They have a microscope. This shit is advanced, man. It's like going down to the nanoparticles. like literally there should be some Nobel Prize winners from these research. uh, you see 1 micrometer here. I saw yesterday in from the 2023 Nobel Prize laureates. One of them was this chemistry professor guy, really cool guy, down to earth guy, and he was saying that what he won the Nobel for was kind of this same thing. It was a mixture of semiconductors with two other researchers, obviously scientists, and yeah, the semiconductors are luminescent, whatever that word is. They are they, they give out some like neon like light, and um, say it helps in quantum computing in the future and in surgery as well. So fascinating stuff. Then we have experimental study, where it's when researchers introduce a variable and study its effects. C is like the interventional study that I mentioned. This is in opposite to observational study. So, for example, does drinking coffee help me get more Anki flashcards done in 1 hour? Yeah, that's a good joke. I have not sipped on coffee, so that's why I'm very slow right now. Um, then we have the cross sectional study. It's a one time observational study that compares the frequency of an associated risk factor to the frequency of a disease. And an example, so again, it's a one time observational study. So the observational studies could be prolonged, but this is a one time observational study, and it compares the frequency of an associated risk factor to the frequency of the disease. Nice. That's why you call it cross sectional. So, do individuals living within 100 miles of the Chernobyl nuclear power plant, an associated risk factor, frequency, have cancer at a higher rate than the general population? This is the effect you want to study, like to the frequency of the disease, higher rate. So is higher exposure, more exposure to the um, Chernobyl nuclear power plant result in higher cancer rate? I'm interested to know the answer of that question, so I'm just gonna put it here in my notes. Uh, uh, to ask from ChatGPT. Okay, then we have a cohort study. The word cohort usually refers to large groups being under examination. So, usually, prospective observational studies that compare a group of people exposed to a risk factor with those not exposed to a risk factor. So, you basically want to compare those who are exposed to the risk factor and those who are not exposed to the risk factor. And do children who grow up in within 10 miles of a fast food restaurant have higher average BMI when they graduate high school than those who did not. So this is different from, keep in mind, this is different from cross-sectional study. Cohort study is comparing two groups of people, but cross-sectional is comparing the frequency of an exposure to the frequency of the disease, the effect, the cause and effect, right? This is two different groups, and saying that cause, that exposure, does affect it on the effect, in, like a exposed group, more or less than the unexposed group. So this is cohort study, right? Then we have a case control study. Should be think about cases. Usually retrospective observational studies that compare a group of people with a disease to a group of people without the disease. So in the cohort studies, you want to see if the exposed group is different than the unexposed group. But in the case control study, you want to compare a group that already has a disease, already has the effect, versus a group that does not have the effect. And so it's a retrospective study. And cohort studies were prospective, so they move forward. But the case control studies is kind of reverse chronological. An example is, do diabetic patients report more job satisfaction than non-diabetics? So they already have the disease, and you're comparing them to another group that does not have the disease, and you want to see if they do report more job satisfaction. So you have to survey them, and they have to think retrospectively. They have to think about the past and see if they are satisfied with their jobs before or not. Okay. Now, here we are starting to see the lab techniques, like the separation techniques. We have the Western blot, which is used to quantify amount of protein after running gel electrophoresis. So I was reading this from the Shemasian blog on the MCAT. The gel electrophoresis. The gel is like a jello, and you just pass the molecules through the jello and see which ones are faster based on their, for example, charge, size, and mass, and even shape. Charge, size, mass, shape. Shape and size, you can put them under one category, I assume. But we'll definitely know more about this. There is a mnemonic here apparently, where it's snowdrop. The W is for the Western blot, that is used to quantify the amount of protein. The N is the Northern blot, and it is used to quantify the amount of RNA. And the S is the Southern blot is used to quantify the DNA. we have triple bonds, and they result in high UV absorbance. Now we are trying to relate the UV spectroscopy. They are higher than the double bonds. Are the double bonds also higher than the UV absorbance? We'll figure that out. Let's for a second go back to UV spectroscopy. You can see that it was used to measure, so you just pass a beam and you record the UV spectroscopy and you use it to see how let me just put these images. So triple bonds have why is there no good graph for comparing bonds and stuff? Oh, this is called the electromagnetic spectrum, the UV invisible. The UV is right here. It's more even frequency than the violets, and it's ultraviolet, right? And the infrared should be, yes, it's before the red. So infrared is less frequency and higher wavelength. Now, let's see if we find reading here. You can see if the n is increasing, it shifts more to the right. It's higher frequency. It's a higher wavelength. What did we study here? The triple bonds have high UV absorbance. Okay, we can just ask the question here: why do triple bonds have higher UV absorbance than double bonds? Is it the same relationship for double bonds versus single bonds? We have the thin layer chromatography, the TLC, right? There are some factors here. There is the RF, which is the distance traveled by the solutes over distance traveled by solvents. It should never be higher than 1. which means the solute should not travel past the solvent. It's impossible. The stronger the interaction between the solute and the SP, the lower the RF. Is SP the solvent something? The lower the distance, the stronger the interaction, because it just stays there instead of traveling far distances. We have MP, which is SP silica gel, which is highly polar. So it's a highly polar silica gel. If it's polar, it means that it's all about charge, right? We're talking about charges here. So the stronger the interaction, the less RF. And MP is organic solvent, which can be polar or non-polar, but is generally non-polar. So if it's about not being non-polar, then you know for a fact that it's not that much about charge, right? So the more charged the molecule is, it doesn't matter. But if it's polarity is, it's all about charge. The polar examples are polar solvents are DMF, DMSO, water, and acetone. And the non-polar ones are alkanes, benzenes, toluene, and whatever this is, diethyl ether. There should be some way for us to know these, or it comes with practice. We'll figure that out. Okay. And we have the isoelectric point, which is the pH when a protein has no electric charge and therefore cannot move in an electric field. So, the isoelectric point is the pH at which the molecule is not charged anymore. The protein is not charged anymore. It doesn't have any electric charge. And therefore it cannot move in an electric field. This can give you clues as to what amino acids compose the proteins. This is how the MCAT frequently tests isoelectric points focusing. That is right. The more conjugated a system, the larger the wavelength light it can absorb. On a UV spectroscopy graph, this looks like a right shift. So more conjugation means that there's more bonds, I would say, right? Like if it's a benzene ring, like a benzene ring has high conjugation, right? So the more conjugated it is, the larger wavelength light it can absorb, which means it goes to the right of the UV spectroscopy graph. The right shift means, you can see here, right? This is kind of conjugation. It's a double bond. So right shift means higher wavelength. Let's add this. Larger wavelength correlates to lower energy according to E equals HF. That is true. And what was H equal to? 1.9 times 10 to the negative 34, I think. Should be right here. H 6.626 times 10 to the minus 34 kilograms meters squared per second. to the minus 34 kg times meters squared or second. I believe it's the same thing as what was the unit for Newton? So F equals ma, which is equal to kilogram times meters per second square. Right. So this is the opposite direction. Good to know. Side thought. What am I thinking to myself? The MCAT denotes statistics with p-values, error bars, asterisks stating it. Error bars, asterisks stating it, just saying it. Sure. Southern blot, snowdrop should be used to quantify DNA. Yes. After running gel electrophoresis. Nice. Single bonds equals to low to no UV absorbance. You can see we kind of answered this question here. So we know that single bonds have almost zero to none, close to zero, low to no UV absorbance. STS page. This is a type of gel electrophoresis that denatures the protein and provides a uniform charge for the protein. This means the proteins are only separated by molecular size. So STS is the name of the denaturant. Right. I believe STS, I saw it somewhere. We'll find it. So again, it's a type of gel electrophoresis. So we have STS page. The page stands for polyacrylamide gel electrophoresis. Polyacrylamide is just the type of the jello they use, and this type of electrophoresis, STS, denatures the protein and provides a uniform charge for the protein, right? And it provides a uniform charge for the protein. What does it mean? Oh, so it kind of neutralizes the charge of the protein. And this means the proteins are only separated by molecular size. So that you can focus on the size only. You just want to remove the factor of charge out of the equation. What does STS stand for? Northern snowdrop should be used to quantify for the amount of RNA after gel electrophoresis. Then we have the native electrophoresis. So this is a type of gel electrophoresis where proteins are loaded to be separated without any changes to the protein. So you do not denature the protein and you just load them. You just throw that protein in there raw, and in order to separate it without any changes to it, they are in their native conformation, right? You don't want to change it, meaning their separation depends on their size, charge, and even structure. So their separation depends on the size, charge, and structure. Size, charge, and structure. Is structure different in size? Yes. Is structure the same as shape? Maybe. Isoelectric point focusing. This is a gel electrophoresis phoretic technique that separates proteins by their isoelectric point. The isoelectric point is the pH when a protein has no electric charge and therefore cannot move in an electric field. So at the isoelectric point, the protein cannot move in the electric field because it doesn't have any charge, right? So the isoelectric point focusing, IP focus, PI focusing. Here, this is a gel electrophoresis technique that separates proteins by their isoelectric points. Yeah, makes sense. PI. In the PI, it is the pH where the protein cannot move, doesn't move, has no electric charge. So it doesn't move in an electric field because it doesn't have an electric charge. We have the ion exchange chromatography. It is a subset of column chromatography that's aimed at isolating charged particles. If you want to isolate a positively charged molecule, think arginine, you will use an anionic negatively charged column. When you're discussing electrostatics, opposites attract. So what are we discussing here? We're talking about ion exchange chromatography. What does ion exchange mean? It's a subset of column chromatography, so we need to know what is a column chromatography. I have seen that years ago back in chemistry lab, but the ion exchange chromatography is aimed at isolating charged particles. So if you want to isolate a positively charged molecule, think arginine. You will use an anionic negatively charged column. You will use an anionic negatively charged column because it's the opposite charge, and you want to isolate the positively charged particle. When you're discussing electrostatics, opposites attract. Ion exchange, chromatography. So you load the samples here. It is a technique for separating compounds based on their net charge. Ion exchange media containing negatively or positively charged functional groups, covalent bound to solid support, yielding either cation or anion exchanger respectively. So you load the samples. There are immobilized anion surface. Anion refers to negative charges. Cations are positive charges. So if you have an anion immobilized surface, then the positively charged protein with immobilized anion surface, they are passed through this thing. They are eluted with low salt gradients like NaCl, and then because you can see the Na plus sodium ions are here, and these positively charged molecules of interest for us are going to, they're eluted with high salt gradient afterwards at the end, and they attach to the chlorines, as you can see here, and the polymer beads with negatively charged functional groups, right? What could be a possible example of functional groups in proteins that are negatively charged? We have two examples. We have the glutamate and the aspartate, right? The glutamic acid and the aspartic acid. And the big red dots here are the large net positive charge, and then the orange ones are net positive charge, the blue ones are net negative charge, and the darkest blue are the large net negative charge. And the protein mixture is added to column containing cation exchanges. Proteins move through the column at rates determined by their net charge at the pH being used. With cation exchangers, proteins with more negative net charge move faster and elutes earlier. Why doesn't it show on the tubes? I have no clue. So you have the elution column, you have the positive molecules and the negative molecules. The positives go faster. Negatively charged proteins bind at low salt concentration. Bound proteins are eluted at high salt concentration. Oh, so you use the low gradient salt concentration, the low salt gradient, to elude the same charged particles that are like the negative you see here. And then the high salt gradient, you elude the positive you elute the positives because they were attracted, right, to the column. They were attached. There's a washing step, there's the low gradient salt, and then there's the elution step. So it all depends what is the charge on the column of the column chromatography, right? The higher the salt gradient, the more opposite charged molecules, proteins that you pass through the column with relation to the column wall itself are eluted, right? So in the first you see here the sodium cation, Na plus, meson, and then protein bearing a number of positive charges. A mixture of proteins in mass buffer is loaded onto the cation exchanger. Positively charged proteins absorb to the media, displacing sodium cations. Repulsive. To avoid drastic ionic strength increase and pH decrease in column microenvironments, applied concentration of absorbing proteins should be less than 5. The maximal protein concentration is 15 milligrams. All these graphs, they fail to fully represent just, okay, the first column, the first tube, you have just, I don't know, water. Like if these beads are negative, then you expect to have negative charges, and then net positive charges, you expect them to elute later. Net positive charges you elute last because they were attracted to the polymer beads with the negatively charged functional groups. But makes sense to me. I think this guy is explaining that, but I'll watch it if needed or at my leisure. Let's have this just. No, what else? So the whole point is to keep in mind that it is for charged particles. You want to isolate charged particles. So if you want to separate arginine, which is a positive molecule, you will use a negatively charged column. An anionic charge column. Gel electrophoresis is a lab technique used to separate molecules, macromolecules, usually protein or DNA, by their size and or charge. So because gel electrophoresis page is just too broad, we noticed that there was a native page where you don't denature the protein, so it's based on both size and charge, and also the structure, the shape of the protein. However, for SDS, because you are neutralizing the charge, it's only based on the size, right? We can see here as well. So because you denature protein, it provides a uniform charge for the protein. So this means the proteins are only separated by their size. We also asked to see how does did we ask how does SDS denature protein? How does SDS denature the protein? So this is done, gel electrophoresis is done by placing the macromolecule at this starting line called a loading well and running an electric current through the gel. So you have a starting line, a loading well, and then you run that thing through the electric current. We also have gas chromatography, used separate via boiling point, which is a proxy for polarity. Boiling point is a proxy for polarity because as things become more polar, they stick to each other tighter. If they are stuck together tightly, they will have to be heated to a greater degree to get them to unstick from each other and become gases. Thus, the greater the polarity, the higher the boiling point. Okay, I just read off of that and paid no attention to it. So, am I boring? Am I boring? Yeah, probably. Who cares? Ha! I'm thirsty, guys. I need to get some water, but our timer is going to be off very soon so that we can take a rest. Let's just finish these. So, with gas chromatography, you separate the molecules via boiling point. So you use boiling points. That should be tough. And it's a proxy for polarity. How is boiling point related to polarity? Right, because when you're more polar, when you have more hydrogen bonds, for example, the higher your boiling point, right? Or is it the opposite? Alcohols have lower boiling points than water, for example, right? Boiling point is a proxy for polarity because as things become more polar, they stick to each other tighter. So this means that water is very polar and they stick together very tightly. If they are stuck together tightly, they will have to be heated to a greater degree to get them unstick from each other and become gases. Thus, the greater polarity, the higher the boiling point. This makes sense? So this should give us the interpretation that water is, give us the reason that water is more polar than alcohol. Now, let's see what we find about gas chromatography. You have a gas flow regulator, you have a sample, injector port, you have the column, and then you have the detector. You also have waste, and boom. You analyze the data. You have auto sampler inlet. Sure. And this is what it looks like. What it looks like. Double bonds have high UV absorbance, but triple bonds have higher UV absorbance, right? Conjugated systems equal to the highest UV absorbance. So the higher than a separate double or triple bond. The conjugated system of double bonds, imagine benzene, absorbs UV more so than an isolated triple bond. We also have column chromatography, which separates chemicals via polarity, uses beads as a polar solvent, which are either polar or nonpolar, depending on what you want to catch. If the molecule you want to catch is polar, like a glutamine amino acid residue, is glutamine is polar, but it is wait a sec. Glutamine is positive charge, right? Because glutamate and aspartate are negative charge. We have arginine, histidine, and glutamine. Not to confuse it with glycine or other ones. You'll use polar beads because glutamine is polar. So keep in mind that column chromatography separates chemicals via polarity. We had is gas chromatography considered column chromatography too? Yeah, because it's just see it is using a column. We saw that there. We do have okay, we'll get back to it, but I wanted to ask a question I forgot. Chromatography uses a mobile phase, which usually contains the chemical of interest, and carries it through the stationary phase, which catches the chemical of interest. As implied by the name, the mobile phase moves, the stationary phase doesn't. So chromatography uses a mobile phase. MP is so MP stands for mobile phase, and SP stands for stationary phase. Motherfucker. That was actually my question. And the mobile phase usually contains the chemical of interest, yes, and it carries it through the stationary phase, of course, which catches the chemical of interest. As implied by the name, the mobile phase moves. The stationary phase doesn't. Of course. Yes, I understand all of that. An experimental study is the only casual experimental study, but it is generally impractical or unethical to carry out. So, for that reason, among many others, you will almost never assign causality on the MCAT. Almost everything will be correlational. So it's all correlational. Wait, so if an experimental study is the only causal experimental study, but it is generally impractical or unethical to carry out. So interventions, experimental, it is generally impractical or unethical to carry out, but I mean, in the real world, there are a lot of experimental studies that take place, right? And they used to take place a lot more, I assume, in the past decade or 2 decades ago. Like nowadays, it's maybe less, maybe even more. I have no clue. We can actually general Q. Are there more experimental studies nowadays or less compared to a few decades ago? So yeah, because experimental study is the only causal study, you will almost never see any causality. Nothing causes the other one. It's all correlational. Okay. Affinity chromatography, it separates via, that point is very, very important. Affinity chromatography separates via a specific tag. This is done by using a column that has a high affinity. What is this specific tag? Tag is the lingo used on the MCAT, but it just means a specific group that will bind to your molecule of interest. For example, if you are wanting to bind the amino acid cysteine, your tag should probably select for SH groups because that is unique to cysteine and creates a strong interaction. I'll come back to the affinity chromatography in a second. We have these functional groups, and their characteristics on the IR spectroscopy. You can see the carbonyl, for example, C double bond with O, has a sharp and deep IR spec, and the resonance frequency is 1700, the least among these. And the alcohol has the most, and amide has the most. They're broad. Amine is shallow, amide is deep. What does the deep mean? It means that the transmission is less, right? If it's sharp, what does a sharp or deep or broad characteristic mean for the IR spectroscopy? Yeah, we need to memorize these. I'll do that later. But for affinity chromatography, you just want to separate the molecule via a specific tag, like a functional group, right? If you want to bind the amino acid cysteine, which has sulfur SH group, right? Your tag should probably select for SH groups because this is unique to cysteine and creates a strong interaction. And with that, you can focus on making a hydrogen bond, right? Is the SH group on cysteine a hydrogen bond? Hydrogen bond. Can it make a hydrogen bond with another functional group in affinity chromatography? Perfect, we're done. So I'll see you at the next study sesh. We have only these 4 categories left, and once we get them over, yeah, these are easy peasy. Then we will just go back on these first ones, and then we can dive deeper more into these topics. For now, ciao.